Okay, so our next topic is sums of two squares. We already know, and we did this before, we already know how to write a number as a sum of two squares. If we can factor the number and as a product of, say, two smaller numbers, and then write each one of those as a sum of two squares, and then the product will be a sum of two squares. Now, here we talk about, again, just a qualitative type of question. Is the given number a sum of two squares, yes or no? And we have a very simple criterion for primes. Let's write it as a prime P, say larger than or equal to 3, is a sum of two squares. If and only if P is congruent to 1 modulo 4. Only if P is congruent to 1 mod 4. And as an example, say P 37 is congruent to 1 mod 4, so 37 is the sum of two squares. And in fact, the second part of the theorem will tell us that there is a unique way to write it. In this case, it's 36 plus 1. 6 squared plus 1 squared. Or 1 squared plus 6 squared is considered to be the same representation. But if I have P is 31, another prime, this is a number that's congruent to 3 mod 4, it's not 1 mod 4, so then this number cannot be written as a sum of two squares. So this number is not a sum of two squares. So a question like this is very easy to answer, even if a number is very large. I just need to check if the number, if this information is available to me, if it's given in the problem, that the number is a prime number, then it's very easy to check. I use this criterion. Check if the number is congruent to 1 mod 4 or 3 mod 4. Now, for a general number, so a general theorem that in particular applies in this case, but it applies in all cases. So again, if I have a number that I know it's a prime, then I just use this criterion. So now for a general number, let's write it here. A positive integer n, now let's say I have the prime factorization of n, say P1 to the A1, and so on to Pk to the AK, a product like this. Can be represented as a sum of two squares of integer numbers. Two squares, if and only if, and only if for each prime, let me say first and then I write it. I look at the prime factors, P1 up to Pk, those that are congruent to 3 mod 4. I look at them. The others I ignore. I look at those that are congruent to 3 mod 4 and I look at their exponents. If I see at least one exponent that's not even, then the number is not representable. Otherwise it is. So let's see how he stated. So the number can be written as a sum of two squares if, and only if for each factor Pj is congruent to 3 mod 4, the following happens. The corresponding exponent
AJ.
The exponent AJ is even. It looks complicated and it has a long statement. So let's review. Let's see several examples. It's going to be easy to use in practice. Example is this number a sum of two squares. Let's say n is 3 to the 4 times 5 cubed times 7 cubed. Is the number a sum of two squares? And the answer is no. Why? Because it's not true that for each Pj congruent to 3 mod 4, the exponent is even. I can see a Pj. I can see a prime. I have three primes, P1, P2, P3 in this case, 3, 5, and 7. I can see this prime, 7, is congruent, so no, because seven is congruent to 3 mod 4, and the exponent of 7 is odd. Is this number 3. The exponent of 7 is odd. So it's not true that for each Pj congruent to 3 mod 4, the exponent is even. It's true for some of them, for instance, for 3. So 3 is congruent to 3 mod 4, is a prime, its exponent is even, but it doesn't have. This, just because there is a prime congruent to 3 mod 4, there is an odd exponent, the number is not representable. It's sum of two squares. Another example. Say let's say 2 to the 6 times 5 cubed times 7 to the 4. Okay, times 11 squared. Is this number a sum of two squares? And in this case, the answer, let's see. Before I give the answer, let's see. I look at the primes Pj's that are congruent to 3 mod 4. 2 is not 3 mod 4. 5 is not 3 mod 4. 7 is 3 mod 4 and 11. These two. Is it true that for each of them, for 7 and for 11, the corresponding exponent is even? Yes, it is true. This exponent is 4, it's even, and this exponent is 2, it's even. So the answer is yes. So this number can be written as a sum of two squares. Even if you see the exponent of 5 is odd. It doesn't matter. Because 5 was not under consideration here. And it wasn't because 5 is congruent to 1 mod 4. Yes, please.
So does it matter that we have 2 because it is neither 1 or 3 mod 4? Does that create any intricacy?
2 itself is a sum of two squares as being a 1 plus 1. If the number is a sum of two squares and you multiply by 2, again is a sum of two squares, as we know, because if we take any number that's a sum of two squares, multiply by a number that's a sum of two squares, we even know how to write it. That's how we did in one of our exams. So anytime I multiply a number by 2, if the number was a sum of two squares, it's still the sum of two squares. So we can multiply by any power of 2. This doesn't change. And that's why in the theorem there's no mentioning of 2. There's no mentioning of 5 either. 5 being congruent to 1 mod 4, because we know that 5 is the sum of two squares, so it won't bother us. Now, if you ask me, write a number as a sum of two squares. That's a different question. We say now in this new exam, we only look at, as I said, the qualitative statement. Is a sum of two squares or not? But if you ask me to write as a sum of two squares, then I can do that. How do I do this? I write this number equals, I take the largest possible square as a common factor. It's 2 to the 6, 5 squared, 7 to the 4 times 11 squared. And then times what? A single factor of 5. A single factor of 5. But 5 itself alone is a sum of two squares. 4 plus 1. So that's our representation. 4 times this is a square, 1 times this is a square. So it's a sum of two squares. And now we can see the difference between this and if we had 3 here, I mean 11 cubed and 5 squares. In this case, if I try to write it as a sum of two squares, I have 2 to the 6, 5 squares, 7 to the 4, 11 squared. Yes, but then I'm left with an 11 and I cannot write this as a sum of two squares. Okay. Any other interesting examples? Yes. How about 10 factorial? 10 factorial. Is this number a sum of two squares, yes or no? And the answer is clearly no. But why? Because you see, I don't even need, in the other examples, we had the prime factorization of the number. It was given to us. In this case, it's not given, but we understand what this number is. It's 10 factorial is the product of numbers from 1 to 10. No, because there is a prime, at least one prime p congruent to 3 mod 4 having an odd exponent. In where? In our number, 10 factorial. There is one prime congruent to 3 mod 4 with an odd exponent. And that makes this number not representable as a sum of two squares. Can you see one prime that has an odd exponent in 10 factorial?
Yes.
And it's 3 mod 4.
7.
7, of course. I don't know about 3. That would be the other option. For 3, we need to check how many factors of 3 we have. Actually, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the number. Let's see how many factors of 3 we have. I have 1 here, another 1 in 6, and 2 other factors of 3 in 9. So we have a total of 4 factors of 3. So that was okay. 3 to the 4, it's good. The exponent is even. There are no other primes congruent to 3 mod 7 that appear here. Just 7. But 7 has an odd exponent because the exponent is 1. So this is not representable as a sum of 2 squares. But if I take this number and send 10 factorial divided by 7, then this number is representable as the sum of 2 squares. Because 10 factorial has a single factor of 7. I divide by 7, I remove this, and the rest is fine. Because the only other prime congruent to 3 mod 4 in this prime factorization is 3. And 3 appears with a even exponent. Okay. So I think it's for the same reason. So in this case, the answer is yes. The answer is yes. Okay, one more question. This number, let's not call it n. A. It's, let's say, 10 factorial divided by 15 factorial and multiplied by 20 factorial. Just out of curiosity. What can you tell me about this number? First of all, is this number an integer number? I take 10 factorial, if I divide by 15 factorial, it's not going to be integer, but then I multiply by 20 factorial and it makes it an integer number. In fact, 20 factorial is already divisible by 15 factorial. So that's an integer multiplied by 10 factorial. Is this a sum of 2 squares? Yes or no? 19 is a prime congruent. Okay, 19 divides A, and 19 square does not divide A. 19 appears with exponent 1. So the answer is indeed no. Okay, so it's clear how we can handle large numbers if we want. We just look at the primes that are congruent to 3 mod 4, see what exponents they have. We see at least one exponent that's odd, the number is not representable. Okay, maybe we should start a new topic in another video.